So we had this grain boundary strengthening mechanisms in which we saw that the smaller the grain boundary, higher would be the resistance to the dislocation motion, and thereby there would be increase in the strength of the material. Then there was solid solution strengthening. We looked into the fact that uh, higher the amount of the solute in the material, as in the case of copper and nickel, higher would be the distortion, lattice distortion that would create a resistance for the dislocation motion, thereby increasing the strength of the material. Similarly, in dispersion strengthening, we looked into the effect uh, dislocation pinning due to the hard particles or precipitates within the material, formation of dislocation loops, which ultimately creates back stress, thereby increasing the strength of the material. So the fourth mechanism that we'll be looking today is strain hardening. What we'll do is that we'll first look into how strain hardening is being achieved. How do you strain harden the material? So let's say you have a tensile sample and you strain the sample beyond the yield stress uh, in a way that this sample is being stretched for tensile load until this yield point is reached, and you keep on stretching uh, beyond the yield point up till this point S1, and then you release the load. You don't completely take it to the fracture point. You release it after a small stress has been applied beyond the yield stress, and this is being performed on an annealed sample. Annealed sample is a sample which is in a stress free state. There are no internal stresses, uh, and it's relatively soft and ductile. So you'll see what is the and how do we prepare an anneal sample in the last half of this course. But at the moment, you need to understand that it's a stress-free ductile sample. So you take a sample, apply certain stress on the material such that it goes beyond its yield point. As the material undergoes plastic deformation beyond the yield point, you would unload the sample. Then you would repeat the same process. You would again strain the sample. Now you would notice that the yield would occur at a higher stress. So if the yield was occurring at, let's say, this point initially, or this stress, now the yield is occurring at a different location at a higher stress. So again, you would take the sample to a stress beyond the new yield stress, and then you would release the load. You would again unload the sample, and then you'll continue doing that. So you would see that after each cycle of loading and unloading, the yield stress is essentially going up. So your yield stress is increasing. That means after each successive plastic deformation, after each deformation, the yield stress increases and material strengthens. All right. So why do you think material is showing such a behavior? Any reasons for such a behavior? Sir, G.
सर ये मटेरियल ज़्यादा हार्ड होगा सर, फिर वो वापस नहीं अपनी स्टेट में उस तरह आता।
Reason for that. It says that as the stress is increased beyond yield stress, material deforms plastically. This means that dislocations are created and dislocations move. So after each plastic deformations, dislocations not only move, they get multiplied at grain boundaries, free surfaces, and the interface of matrix and secondary particle. So each successive deformation, as you take the sample beyond plastic deformation, dislocations are created and dislocations get multiplied at the grain boundaries and the free surfaces or the interface of matrix and secondary phase particles. But high dislocation density, that means higher number of dislocation, does not explain high strength. High strength is explained when dislocation motion gets difficult. So strain hardening is not just the number of dislocations getting increased. It is not that number of dislocations increases, that's why you are getting a hardening effect or strain hardening effect or strengthening effect. It is basically the number of dislocations that are created, they repulse each other and they impede motion of each other. What happens is that dislocations they cross each other, they entangle each other. ये आपस में एक दूसरे के साथ इंटैंगल होके एक दूसरे की मोशन को मुश्किल बनाते हैं. Strengthen the, that's why they strengthen the material. So dislocation intang जी.
सर वो जो आपने सर रिपल्स अदर वाला सर ये पार्ट रिपीट कर देंगे सर जरा सा सर ये समझ नहीं.
That means अगर एक dislocation इस direction में इधर move कर रही है and there is another dislocation that is present over here, तो it would repel, it would basically create a back stress and resist the motion of dislocation, this dislocation one in this direction. All right.
सही सर.
ठीक है. जिस तरह आपने देखा था कि हार्ड पार्टिकल्स के गिर्द लूप बन जाते हैं, these loops create back stresses. All right. अगर यहाँ पे कोई डिसलोकेशन है, इधर मूव करना चाह रही है, तो दिस लूप वुड act as a further resistance. Initially, there was only a particle that was a resistance. Now there is a loop around this particle which is also acting as a barrier to the dislocation motion, or it is the repulsion effect to this dislocation motion. Clear?
यस सर समझा.
So dislocations entangle with one another during cold work. Cold work is you are basically doing this loading, unloading cycle, loading, unloading cycle at room temperature. So when you are deforming the material at room temperature, you refer to the process as cold working. All right. So dislocation motion becomes more difficult during the cold work, and if you see over here, these are basically entangled dislocations. So as they get entangled with each other, इनका मूव होना मुश्किल हो जाता है. ये ऐसे ही है जैसे there is a chaos caused by people in this region. कुछ इधर जाना चाह रहे हैं, कुछ इधर जाना चाह रहे हैं, कुछ इधर जाना चाह रहे हैं. अल्टीमेटली क्या होगा? They will not be able to move anywhere. So they'll keep on pushing in this region, creating the dislocation motion or creating their own motion further more difficult. So as the dislocation motion becomes difficult, it is actually material getting or gaining the strength. All right. Now, strain or work hardening occurs by dislocations interacting with each other and with barriers which impede their motion. So it's simple enough. They are getting entangled with one another and the barriers and making each other's motion difficult. Dislocation density increases with strain. This is basically the prime reason for strain hardening. So if we look at the dislocation density formula, it is basically the total length of dislocation divided by the unit volume in which that dislocation length exists. And it has been further uh, explained that for an annealed sample, which is stress-free, soft sample, ductile sample, the dislocation density is about 10 is to power 5 or 10 is to power 6 centimeter per centimeter cube of the material. And for a strain hardened or cold worked material, this dislocation density it doubles. It is about 10 is what 10 to 10 is what 12 centimeters per unit per centimeter cube of the material. And what is cold working? As I had already mentioned, cold working is room temperature deformation. Some of the common cold working operations which involve change in cross sectional area, they include forging. You will study them in your manufacturing process course. But just to give you an idea, there is a blank that is being placed in the die. Force is being applied onto
यस सर
this.
सर ये हमने पढ़ा है पूरा प्रोसेस सर.
All right, so you have studied forging process, rolling processes where you are passing the rod through the through the rollers, and you reduce the cross sectional area. Similarly, drawing is where uh, uh, you are pulling the wire through a die and reducing its cross sectional area. And similarly, extrusion is where you're passing a billet through the die and reducing the cross sectional area. So these four processes, as you have mentioned, you have studied. Uh, the only thing that you'll be interested over here is the percentage cold work. Percentage cold work is basically the reduction in the cross-sectional area with regards to original area multiplied by 100%. This is percentage cold work. And this cold work is basically related to the dislocation density. Higher the percentage cold work, higher the dislocation density, and higher would be the increase in tensile strength. So if you see three samples over here, one with 0% cold work, one with 4%, and the other third with 24%, you would see that the yield strength is increasing. And not only yield strength, it is the tensile strength which is also increasing. But the ductility of the material is decreasing. So if you see from 0 to 4 to 24%, your ductility is essentially decreasing. And the reason being, as the dislocation motion becomes difficult, the material gets more brittle. So there would come a time that material would just fracture instead of plastically deforming. If we talk about copper and we say that copper rod initially having a dia of 15.2 mm is cold work to 12.2 mm, and we see that the percentage cold work is initial area minus final area divided by initial area, and the percentage cold work comes out to be 35.6%. So for a cold work copper sample having this much of cold work being performed onto it, what is the yield strength, what is the tensile strength, what is the ductility? So in order to do so, we'll focus on about 36% cold work sample of copper would have a yield strength of 300 megapascal as compared to 0% having a yield strength of about 200 or 150. Similarly, the tensile strength, you would see the tensile strength going to 340 megapascal as compared to about uh, 220 for a 0% cold work sample. On the contrary, you would see 44 or 43% ductility decreasing to about 7% as you cold work the sample from 0% to about 35.6%. So this is the effect of cold working on the materials. Now the last thing that we have to look into is the effect of temperature. It says that as you increase the temperature, the ductility of the sample is increasing from minus 200 to 25 degrees centigrade. The ductility of the sample has increased tremendously, and the yield strength and tensile strength decreases with the increasing test temperature. That means the testing temperature or the temperature has an opposite effect on the tensile strength and the yield strength. The reason being, if you remember, increase in temperature basically increase in equilibrium number of vacancies. All right, and these vacancies help dislocation move past the obstacles. How? Let's say you have a dislocation over here and it has to move on this plane, but there is an obstacle over here, which
आपको दो
is
हज़ार मिले.
Sorry, sorry. Gee, is there a question? So, if there is a dislocation over here and it is having an obstacle in its path, the dislocation would get trapped due to this obstacle, which essentially increases its strength. But if we increase the temperature, what would happen over here would be that initially the atoms which were over here, by increasing the temperature, these atoms would move away and create vacancies. And these vacancies would now create an alternate path for the dislocation. So dislocation would move upwards over here and it would glide past the dislocation, the obstacle on a parallel plane. So on a parallel plane in the same direction, the dislocation would glide past the obstacle, thereby making the dislocation motion easier. Thus, it is due to temperature vacancies were created, and these vacancies essentially help dislocation move. Thereby, it can be said that the temperature basically facilitated the dislocation motion, and when the dislocation motion becomes facilitated or easier, plastic deformation becomes easier, so you will see a higher deformation at a higher temperature. All right.